All right. So let's talk about sampling distributions. When I'm doing a sampling distribution of p hat, we check to see if it's approximately normal by doing our large counts, n times p and n times 1 minus p. The center will be whatever the true proportion, whatever p is. The standard deviation we calculate by doing the square root of p times 1 minus p over n. This is hugely important. You have to check the 10% condition before you actually do the calculation for standard deviation if you're sampling without replacement, which is most of the time when we do sampling. They will never tell you, make sure you check the 10% condition. They'll just say, what is the standard deviation? But you have to include the check. So this is just a, you have to know to do this before you plug numbers into that formula. And then we've talked about normal probabilities before. We've done normal CDF, so I'm not going to spend a lot of time on this. So let's go check out the check your understanding, but I want you guys to reference these quick notes, especially over here in this left-hand box, as we are going through and answering the questions in the check your understanding. According to the American Dental Association, 8% of adults have never had a cavity. A dental graduate student contacts an SRS of 1,000 adults. What is an SRS? Simple random sample. So what's my sample size? 1,000. Contacts an SRS of 1,000 adults and calculates the proportion, p hat, in this sample who have never had a cavity. I want you guys to do number 1 and number 2. Use the notes up in the quick notes box. I'm going to give us about 2 minutes to do those 2 before we go on and do numbers 3 and 4. I want to make sure that 1 and 2 are correct before we go on and do numbers 3 and 4. You will need a graphing calculator for most of the problems that we are doing today. So if you don't already have one, please go and grab one. You're welcome. You're welcome. And N is the sample size, yes. N is the sample size. What is the mean? 0.08. Whatever P is, that is the mean of P hat. Before you can actually do the standard deviation calculation, what do you have to do? Before you actually do the calculation for standard deviation, what do you have to do? Check the 10% condition. So how do I check the 10% condition? Less than. Less than. Large counts, we want greater than. 10% condition, we want less than. So what is our sample size here? 1,000. So 1,000 is less than or equal to
All U.S. adults.
Yes, 0.10 times all U.S. adults. Is that a reasonable assumption to make?
Yes.
Yes, so we are good. We pass our 10% condition. That means we can plug into the formula. So what do I want underneath the square root to calculate my standard deviation? Yes, 0.08 times 0.92 over 1,000, all underneath my radical. And we get approximately what?
0.0086.
Yep, 0.0086. What do I need to do to be able to answer number 2?
Check if it's normal.
Check if it's normal.
Is it big counts?
Large counts. 10% is to make sure I can use my standard deviation formula. Large counts is what we do to check to see if it is approximately normal. How do we check large counts? N times P is greater than or equal to 10. What is N times P here? 80. 1,000 times 0.08 gives me 80. That's at least 10, so we're good there. Is that enough? I still need to check what? N times 1 minus P. What is N times 1 minus P? What does that come out to? 920. That's at least 10. And so we can say confidently that the shape is approximately normal. Please do not say normal. If you say it's normal without the approximately in there, you are implying that it is exactly normal, and we don't want to do that. All right. Now I want you guys to go and do just part 3, just number 3. Find the probability that the random sample of 1,000 adults will give a result within 2 percentage points of the true mean. What do they mean by within 2 percentage points of the true mean?
0.06 and 0.0.
Yeah, not necessarily 2 standard deviations. I'm looking at 2 percentages. What is the true mean again? 0.08. So within 2 percentage points would be between what numbers? Yeah, 6%, 0.06, and 10%, 0.10. So I want you to do that on number 3. Because we said that this was approximately normal, what do you have to make sure to include on number 3? Drawing. Draw your normal curve. I'm only going to give about a minute and a half or so for you guys to do number 3. I'll move around the room in case you need help with any piece. We're not doing number 4 yet, though. It says within 2 percentage points of the true proportion. This is the true proportion. Yes. So I want to know, what is the probability that the random sample has a proportion between these 2 numbers? And we said that this was approximately normal. So you're going to start with your picture. Yes. So your picture should look like this. We want it shaded in between 0.06 and 0.10. Don't forget the big capital N. That means this is a normal distribution or approximately normal distribution. Make sure you label the mean and standard deviation. Probability notation. What would my probability notation look like? How do I say probability of? Big capital P, and then parentheses, 0.06, less than or equal to, how do I say sample proportion? P hat, less than or equal to 0.10, yes. And we're going to do a normal CDF for this. What will my lower bound be? 0.06, coming from right here. It's the left-hand edge on my picture. Make sure you label that as the lower bound. What is your upper bound? 0.1 or 0.10, yep. And then what other two numbers do I need?
0.08 and 0.0086.
Yes, mean and standard deviation, 0.08, 0.0086. Please make sure you are labeling these pieces when you write them down. And then you pop that all in your calculator, and you get about what? 0.979, 0.98, depending on how you round it. I'm okay if you write down 0.98. If the sample size was 9,000 instead of 1,000, how would that change the center, the shape, and the variability? Let's talk about shape first. What'd you say? Yep, I'm reading number 4. If the sample size were 9,000 rather than 1,000, how would this change the shape, center, and variability of the sampling distribution of p hat? So Aiden says that it would still be approximately normal. How can I check so that I know that? Large counts. So what do I actually calculate to check my large counts?
The probability of success times population is greater.
Yes. N times P is greater than not 0.10, but 10.
And then n times 1 minus.
And N times 1 minus P. So what is N this time? 9,000. What is P?
0.8.
Yep, 0.08. So what is 9,000 times 0.08? 720. That's at least 10. So we're good there. And then we have to do N times 1 minus P. So what am I actually multiplying?
0.92.
Yep, 9,000 times 0.92. And what do you get when you do that?
No, it's definitely greater than 10.
Yes, 8,280, which is definitely bigger than 10. So now I know for sure that the shape is the same, still approximately normal. What would the center be? Center is still going to be 0.08. My true proportion didn't change. It doesn't matter how big or small my sample is, that true proportion will be the mean of my sampling distribution. Will variability stay the same? It's going to decrease. What do I have to do before I can just plug and chug on this formula? %% condition. I have to make sure that my sample size is less than or equal to 10% of my whole population. What is the sample size this time? 9,000. So I have to check that 9,000 is less than or equal to close. There's just one piece missing. 9,000 is less than or equal to 0.1 times all U.S. adults, 10% of all U.S. adults. Is that a fair assumption to make?
Yes.
Yeah. Yeah, it is. So now I can plug and chug in my formula. Numerator stayed the same, 0.08 times 0.92. Denominator got quite a bit larger. So what does this come out to be? What'd you say? 0.002859 or 0.0029. I rounded. How does this number compare to our original standard deviation?
Much lower.
Lower.
Much lower. By a factor of what?
9.
By a factor of 9. Did we take this and divide it by 9 to get this? No. But I like the path that you're on. What got bigger by a factor of 9? The sample, which is where in this formula? In the denominator. The numerator didn't change, so it's like the numerator got multiplied by 1, right? The denominator got bigger by a factor of 9, but this is all underneath a square root.
3.
Did we times that by 3 to get that?
0. 1/3.
1/3. 1/3. The numerator didn't change, so again, it's like the numerator got multiplied by 1. The denominator got multiplied by 9, and then it's all underneath the square root. So I do the square root of the numerator and the square root of the denominator. I get 1/3.
Is it still 0.08?
N got multiplied by 9, so sigma is 1/3 of what it used to be.
Do we have to write that down every time?
You do not have to write that down every time, no. But there is a question on the homework where N changes but nothing else changes, and I want to know how the standard deviations are comparing. So on those questions, you will have to say that, but typically, no, you don't need to say that. All right. Let's flip this now to page 13.
Tomorrow is every class short or just
No, just this one
by 17 minutes?
by 17 minutes. All right. You guys also, as we flip to page 13, you're going to need a device now. If you have a Chromebook or a computer or a tablet, that would be best. If all you have is a phone, that will work, but not as easily. So if you have a computer or a tablet, please pull those out and power them up. Go to Canvas. If all you have is a phone, I can show you some workarounds to make this work, but it is much, much better if you can be on a tablet or a computer. All right. While you guys are getting those things out and powered up, we are going to compare orange candies still, but between Skittles and M&Ms. Do Skittles or M&Ms have more orange candies? I believe that Skittles have a higher proportion of orange candies than M&Ms. Mrs. Bolliton believes the opposite. So who's correct? We're going to take a simple random sample of 50 M&Ms. I have an app that'll do this, that is using the company's actual data. And we're going to do a different simple random sample of 50 Skittles. We're going to calculate the proportion. How do you calculate a proportion? Yeah, we're going to do however many we find of interest divided by our sample size. In this case, our sample sizes are all what? 50. Our sample sizes are 50. So you're going to count the number of orange candies in your sample. You're going to divide it by 50. For the M&Ms, you'll put it on this line. For the Skittles, you'll put it on this line. I'll show you where these are in just a minute. You're actually going to do 2 samples for M&Ms and 2 samples for Skittles. All right? So let me show you exactly how to do this. I need you to go to Canvas. Once you are in Canvas, I need you to go find today's date underneath Chapter 7. So go to Canvas, go to Modules, go to Chapter 7 and find today's date. It's titled Differences in Sample Proportions. And if you scroll down, underneath task number 3, there are 2 different links. You're going to use both of them. When you click on, I'm going to use the M&Ms as an example. You're going to click on the M&Ms, and it takes you to a page like this. There are 50 M&Ms. This is a random sample here. You're going to count the orange ones. You're going to divide it by 50. You're going to write the number down on the line. Do you see this circle arrow right here? After you get your first proportion written down, you're going to click this, and that will select a new random sample. You're going to do the proportion of orange again. After you do that for M&Ms, you're going to go back to Canvas and click on the link for Skittles, and you'll do 2 samples for Skittles as well. Number of orange divided by 50, number of orange divided by 50. If you have any questions, I'll be moving around the room to help you with this piece, but we're only going to take about 2 to 3 minutes for you guys to grab your samples.
Twice for M&Ms and twice for Skittles.
Twice for No. You're going to write your first proportion here and your second proportion here, and then first proportion here, second proportion here. All right. All right, you guys are all on computers or tablets. Wonderful. Yes. Absolutely. Yes, you're going to do M&Ms minus Skittles. All right. So this won't show you the whole thing, and it won't let you scroll. So what we need to do. What browser are you in? Here we go. I'm going to click on this. Now you can see it all. Come on. There you go. All right. Okay, so this is a random sample. Have you counted your orange? Okay, count the orange and divide it by 50.
12.
Okay, you're going to divide that by 50. You got 11? I thought you said you had 12. Okay, no worries. So you're going to write that number down on this line right here.
All right.
Like if you add
11 out of 50 or the 0.22?
0.22.
All right.
All right, now you're going to do it again.
I'm saying like if you get like
Do it again and write that number down here.
8, 10, 12, 13.
Nope, that's your M&M, so you're going to write it down here. Nope, divided by 50. Yep, write it down as a proportion. All right.
Oh, for the
And now you're going to go do the exact same thing, but with the other link for Skittles. All right. I'm going to come around and grab somebody's data just so that I have some numbers up here to be able to talk about. Please don't write my numbers down. You should have your numbers written down on your page. You are going to be working with your data. I'm going to steal your numbers because it sounded like you were done. Okay, so you had, did you do 2 samples?
Yes.
Of M&Ms and Skittles?
Yes.
So what is...
Oh, it was sample 1 and sample 2.
You're doing 2 samples.
Okay, my bad.
That's okay. So I'm going to grab one of yours. You had 0.38 here and 0.46 over here. All right, and I'm going to steal somebody else's number. After you get both samples of M&Ms and both samples of Skittles, you don't need your computer anymore. You had 0.28. Where did that come from?
That was.
You're not combining those. You're doing a decimal for this and a decimal for this. Mm-hmm. All right. Everybody should have 4 numbers written down. You are not combining your samples together. You are not combining your samples together. You have a random sample of M&Ms. This is the proportion that somebody got for their first sample. This is the proportion that they got for their second one. This is what they got for their proportion of Skittles that were orange. This is what they got for their second one. So this right here is a p-hat 1. It's a sample proportion from population 1. This is also a p-hat 1. This came from our second population, so that's a p hat 2. That's a sample proportion from the second population. This is a different p hat 2. I want to calculate the difference, M&Ms minus Skittles. So we're doing p hat 1 minus p hat 2. If you have not already calculated this, please go ahead and do that on your page. So it needs to be M&Ms minus Skittles. M&Ms minus Skittles. Skittles is p hat 2, yes. So for the first one, I got negative 0.08. For the second one, I have negative 0.04. Are they all guaranteed to come out negative? No. This is a p hat 1 minus p hat 2. This is a different p hat 1 minus p hat 2. I'm going to come around and get your two differences of proportions, and we're going to make a dot plot out of it. All right? So I'm going to come around the room and get those from you. So negative 0.08, negative 0.04, negative 0.1. Anthony, your other one was 0.1. Yes, you can put your computers away once you have your samples. Negative 0.02 and 0.1. You had negative 0.06 and 0. You have 0.10 and 0.16. All right. Shh. Please work on copying this dot plot into your notes as I'm moving around the room and getting people's proportions. Thank you. You had negative 0.13 and 0.29, which is actually off our graph, so we're just going to put it over here and we're going to label it 0.29. All right. You had 0.2 and 0.1. 0.2 and 0.1.
Isn't that like a coinkydink?
Right. You had negative 0.1 and 0.2. Please copy the dot plot into your notes. You had 0 and 0.02. You have 0.08 and 0. Guys, copy the dot plot into your notes, please. Copy the dot plot into your notes. You had negative 0.12 and 0.2. No, 0.10, sorry, my bad.
I got 0.04 and negative 0.06.
That sounds great. Thank you.
So negative 0.02 twice.
There we go. All right. Copy this into your notes, please. Copy this into your notes. I missed one of your dots?
Negative 0.16.
Oh, thank you. There we go. All right. Copy the dot plot into your notes.
This eye is way worse than this eye.
Each one of these dots is a different p hat 1 minus p hat 2. Each one of these dots is a different p hat 1 minus p hat 2.
So how do we word that?
You would like to
Exactly like that, each one is a different.
Yep, I'm just drawing arrows to them so that I understand that each one of these is a different difference in sample proportions. So this thing right here is the sampling distribution of p hat 1 minus p hat 2. Is this the full sampling distribution? No, this is a partial sampling distribution. What would it take if I wanted the full sampling distribution?
You need every possible combination of M&Ms, every possible combination of Skittles, and every possible combination of the differences.
We would need every single possible random sample of 50 M&Ms and the proportion of orange. We would need every possible random sample of 50 Skittles and the proportion of orange. And then I would need to do every possible difference of those.
AKA, it's insane.
Yep.
This is why we don't
So,
do
what does each dot represent? Yes. We have one random sample of M&Ms, a different random sample of Skittles, and the difference of proportions calculated from these samples. I want you guys to take your best guess. It's okay if it's wrong. Take your best guess down on number 4 for the shape, the center, and the variability. I'm only going to give about a minute, and it does not matter if it's wrong. I want you to take your best guess as to what you think the shape, the center, and the variability is. Answer question number 4 with your best guesses. On number 4, I want you to use the dot plot. Use the dot plot.
I'm pretty sure it would have a pretty big density.
What'd you say? Describe.
That or something, I don't know.
I'm gonna come pick on you and write your answers down.
Wait, what?
I'm just
Like what?
okay.
I'm not even gonna try.
Is it so? Wait. One random sample of M&Ms, another random sample of Skittles, and the difference of proportions calculated.
The difference of proportions calculated from these samples. All right, I'm picking on different people for their answers on this. You do not and should not write down my numbers, but we're going to talk about these in just a second. So I'm just stealing them from random people.
Don't take my
It's okay. All right. So at least one person said they thought the shape was approximately normal. Somebody else said they thought the center was about negative 0.01. Let's look at that. Negative 0.01 would be here. What do we think? No. Where would you want to move it to? 0.1? 0.03? 0.01, 0.03, I could go with that. I already told you it doesn't matter if your answers are wrong here. It doesn't matter if your answers are wrong, as long as you tried. Because we're going to learn how to calculate this precisely. Let's go ahead and flip the page over to page 14. And let's talk about how to actually calculate this precisely for the full sampling distribution, even though we don't have the full sampling distribution. So when I'm talking about just one sample, how do we determine the shape? Large counts, yes. Large counts. How do we find the mean when it's just one sample? N times P is when it's binomial. This is a sampling.
It's just P.
Yes, it's just P. So the sampling distribution of P hat has a mean of whatever the true proportion is. How do we calculate standard deviation? Square root of n times, or sorry, not n times, it's P times 1 minus P over n, yes. And somebody mentioned what we need to do before we actually plug into that. What is that? 10% condition. Always got to check your 10% condition before you plug and chug with this. All right, so according to company data, and this is what the apps were based on, this really is the real company data, I'm not making this up. M&M's claims that their true proportion of orange is 25%. And Skittles claims that their true proportion of orange is 20%.
Okay.
So how do I check the shape for M&M's? Large counts. So what do I need to actually do? What should I write down in this box? NP, what is N and what is P? N is 50. 0.25, what does that come out to be? 12 and a half, that's at least 10. So far so good. $50 times 0.75, which is 37.5, that's at least 10. So what is my shape here? Approximately normal. Please go ahead and check the shape for Skittles now. Check the shape for Skittles. Thankfully, they don't grade us on spelling, which is really good because I'm really bad at spelling.
I've seen people do 2x's as well as
Yeah.
1x.
Is Skittles approximately normal?
Yes.
Because N times P is what? N times P is exactly 10. So we are like barely meeting this condition, but we do meet it. What is N times 1 minus P? 40. So we get approximately normal. What is the mean for my M&Ms? 0.25. The mean for population 1, for P hat 1, sampling distribution of P1, is just whatever P1 is, which is 0.25. What's the mean for Skittles? 0.2 or 0.20. Before we do standard deviation, we got to do what? 10% condition. So for my M&Ms, to check my 10% condition, what do I need to actually write down? 50. It's less than or equal to 0.1. All M&Ms. Is that a fair assumption? Yes. How do I check 10% for Skittles? Same thing, 50 is less than or equal to 10% of all M&Ms? All Skittles. 50 is less than or equal to 10% of all Skittles. All right, so I want you to calculate the standard deviation for both of these. Calculate the standard deviation for both of these. What's my standard deviation for M&Ms?
0.061.
0.061. I took it out one more decimal place, but I'm fine if you do 0.061. Does anybody have a standard deviation for Skittles for me? 0.0566, 0.057.
No.
I'd take either one. We only have 2 minutes until the bell, so we're not going to go any further on this. We need to finish up 6 and 7 tomorrow, and then we need to do the quick notes and check your understanding on page 15. We should be able to easily get those pieces done. I should also be able to finally pass back your tests.
Oh, so we're good on time?
We are good on time right now.
Fantastic.
Whatever extra time we have in class tomorrow, you guys can use to work on the homework. When is the homework due? Monday, the day we get back. So like I'd be setting reminders on my phone and stuff if you don't get done with it during class time tomorrow. We have covered most of what you need to do that homework. We're going to finish it up tomorrow in class. And then homework is due when we get back. This does also mean that I have pushed the test back by a day. It's not going to be on Monday the 8th. Now it's going to be on Tuesday the 9th.
Let's go.
Test will be on Tuesday the 9th.